So the title of my talk today is kind of paradoxical because we usually think of quantum as describing very small things like atoms and light, particles of light, and the universe is the biggest thing we know of. But these come together, and I'll give you numerous examples in this lecture of how we do know that the universe is quantum, and understanding its quantum nature is probably the key to understanding it, full stop. So I love this picture, which is from the Dolomite Mountains. Shows a cute little house surrounded by this spectacular scenery with a backdrop of our galaxy, the Milky Way. And this really captures how we live. We're so fortunate to live on a hospitable planet and also to be able to see above us spectacular illustrations of the basic laws of nature. We learn from the sky, we learn from the universe, and that knowledge is incredibly important and fruitful for the future. So Minyoung asked me to say a few words about Galileo. Of course, it's difficult to only say a few words. This is somebody who really started the subject of experimental science in the period of the Renaissance, who insisted on reasoning for himself rather than believing some catechism. And you see he's holding a telescope, so he looked at the sky, but he also did experiments. And what he learned is that the universe, as far as he could see it, obeyed incredibly simple laws. And that's the theme of my lecture too, understanding the simplicity and economy of nature. So this is a page from one of his books. There's a copy which I've held in my hand of this book, which was Isaac Newton's copy in Trinity College. And you can see Galileo's little illustrations of the moons going around Jupiter. And he proceeds by analogy. You see these little stars are the moons, and they're obviously orbiting Jupiter. He sees them at different times, different positions. He figured out, well, if the moons are orbiting Jupiter, maybe the Earth is orbiting something else, the sun, and maybe the planets are going around the sun. And so this applying the same ideas and principles from one realization in nature to another was very profound and very fruitful. But not only that, he did experiments on falling brass balls, and he saw, and I'm going to do a little demonstration to you now. Here's an orange. And if I throw it in the air, I hope you can see that. It follows a very simple curve, and that curve is the simplest curve in mathematics. It's not a straight line, it's a parabola, y equals x squared. And Galileo realized that falling balls, or projectiles, follow parabolas, an amazingly simple result. So here is a sketch from his notebook, and you see he rolls the balls down an inclined plane, and then they fall off the edge of the table onto the floor, and he measures the distance on the floor where they fell, and by starting them off higher and higher, they roll down faster and faster and go further out. And this was a nice article in Scientific American, which repeated his experiments using modern equipment and a stroboscopic light. And here they compared their own experimental results with Galileo with very, very good agreement. And they found a consistent difference from theory of about 1 or 2% in the negative direction, which is that they believe due to the effects of air resistance. So Galileo performed these amazingly simple experiments, and he learned this amazingly simple fact about nature, I should say amazingly accurate experiments given that he was the first person to do this. And he learned amazingly simple truth that a parabolic trajectory is the behavior of a projectile. Now let's go a little bit forward to very recently. This is our picture, a very recent picture of the sun made by the ESA solar orbiter. And so looking at this, it's a very hot body. It's very beautiful. There's a lot of plasma physics going on. And of course, we're looking at it from the outside. Now, we're of course located in the universe. The sun is at the center of our part of the universe, our solar system. We're going around it. Here it is. As we look outwards, we're actually inside something that's a bit like the sun. We're surrounded by a very hot plasma of charged particles and radiation, this red ring around us. It's much bigger than the sun. It's about 14 billion light years in radius. And as we look outward, we see the light that it emits. So literally, we're living in the middle of this hot, spherical, sun-like surface. And when the light was emitted, in fact, the temperature was about the same as the temperature of the sun today, within a factor of 2. And that temperature from that light from the hot Big Bang itself traveled through space. And as it traveled, it passed through galaxies and stars as they first formed and came to our telescopes. So we're amazingly fortunate to be living at a time where we can literally see the whole visible universe, learn about the laws of nature, and learn about our origins. Now, this is the picture in space. As we look outwards in space, we see obviously more and more distant objects, and we're seeing them earlier and earlier in the history of the universe, just because light travels at a finite speed. And you might wonder what the blue ring is. The blue ring is the initial singularity. So that's the beginning of everything. And that's very weird when you look at it in this picture, because it looks like the biggest thing, but actually it's also the smallest thing, because if you follow this region of the universe backwards in time, and it doesn't have an edge here, that's just following the region of space as it expanded out of the Big Bang, but we're cutting off the picture just to make it visible. So this is the picture of the universe's evolution in time. Here's the Big Bang, here we are, and this is the history of the universe. So the Big Bang singularity is this point from which everything came. And as the universe came out of the Big Bang and expanded and cooled, the atomic nuclei were formed, and then atoms were formed as electrons were bound onto atomic nuclei. And this hot plasma surface we're looking at from the inside is around about here. Then there's an epoch called the Dark Ages, the cosmic Dark Ages, where nothing much is going on. And then stars and galaxies begin to form, and here we are today. Now, if we follow the trajectory of light, which was emitted by that hot plasma, it's something like this. You see instead of traveling at 45 degrees in this picture, which it would do if space was static, it follows this curved line, because as we go backwards in time, space itself is shrinking. And that's how this blue circle on the outer edge of the picture, if we follow it, the universe backwards in time, that blue circle shrinks. And that blue circle represents what the light would see if it traced all the way back to the Big Bang. Now, so the universe is very dynamic. It's finite in space, in time, at least the space we can see, the part of it we can see, finite in time. And as it expands, the light which is traveling through it changes because it is stretched by the expansion. So here's a light wave as it was emitted by this hot plasma, and then it travels through space towards us. As it's traveling, it's being stretched. And when we receive that light, it is microwaves. So we are literally in a microwave oven. The wavelength of these waves that came off the Big Bang is millimeters and centimeters, just like the waves in your microwave oven. Now, this experiment, the satellite, really initiated the modern era of cosmology, which, as you'll see, has become quite precise and is giving us just a wealth of information about basic physics. This satellite, I was fortunate to go to the first presentation of results of this satellite in Princeton, where somebody showed this graph, and the audience gasped, because this is the kind of graph you very rarely see in a physics experiment. Normally there are error bars and uncertainties in the data. Here the curve is the green one. It's been known, the curve has been known since 1904, I believe. It's one of the most basic curves in physics, the Planck spectrum. The red crosses are the data, and they just line up beautifully. And in fact, in the lower curve, you see all these red dots are shown with the difference from the Planck spectrum. And these red error bars are 50 sigma error bars. Okay, so this is an extraordinarily precise fit. And really, this experiment marked the transition of cosmology from a rather hand-wavy science to, in some cases, a very precise one. Now, the wonderful thing about this curve is that the curve was forecast by Max Planck, the founder of quantum mechanics and Planck's constant, in his efforts to explain electric light bulbs, because he was employed to do that by the German Bureau of Standards, to explain what is the color of a light bulb and how do we optimize the color. And it turned out the answer to this was to understand that light really consists of quanta, little packets of energy. And Planck proposed this, what's called the Planck spectrum, partly on the basis of that data. This was then argued mathematically by Einstein and others. And this really lies at the origin of quantum mechanics. So I'll just explain roughly how the Planck spectrum works. You see, you've got a hot body, like a light bulb or the sun or the plasma of the Big Bang. And you want to explain how it exists in thermal equilibrium, how it exists when it's hot. Now, there is a problem because light is a wave, and waves come in all wavelengths. And Maxwell's theory of light allowed waves of any wavelength. So you can have radio waves, which are meters or hundreds of meters, microwaves, you can have light waves, you can have X-rays, which are very short wavelengths. The theory allows waves of any length down to zero. Now that's a problem. Why? Because if you treated the theory as it came to us from Maxwell, and you put it in contact with a source of heat or energy, light waves would be excited down to all wavelengths. And there are just so many waves of tiny size, they would absorb all the energy. So nothing could ever be hot in Maxwell's theory of light, because the tiny wavelength waves would just absorb all the energy. So this was known as a disaster. And therefore, and it prevented you predicting the color of a light bulb. So Planck introduced this Planck constant. And what this does is very clever. It says, no, you can have light of all wavelengths down to zero, but there's a price. The price is that light only comes in packets of energy. The shorter the wavelength, the bigger the energy packet. And so it becomes very difficult to excite short wavelengths because they're very costly. And this is the energy cost. Planck's constant times the frequency of the light is the cost of one packet. And by introducing this concept, Planck made this curve die exponentially at high frequency. And this enables light to exist in combination with a hot body. So this really was the origin of quantum mechanics. It too comes at a price, as we'll see later. Because if you say light comes in packets of energy, you quantize the light, then it turns out that the vacuum, empty space, these quanta are not zero, okay? Empty space is also full of little quanta of light, and they have what we call 0-point energy. And when you add up all those energies, guess what? You get infinity. And that's still a very deep paradox, which I'm going to give you some clue about how we might resolve. So this spectrum was very fundamental and continues to be very fruitful in basic physics. Now, more recently, the Planck satellite, named for Planck, mapped the whole sky. So we are inside a sphere, hot sphere, which surrounds us. And this satellite observed the interior of the sphere from our vantage point. And this is, then the sphere is mapped onto a plane, like in the usual way we make atlases. And here's the picture of the hot Big Bang from the inside. Very spectacular. You see the structure. These are the very earliest structures in the universe. This is the most ancient fossil remnant of the Big Bang. And these little variations in density are what gave rise to the galaxies and the stars, which we now see all around us. So theory, before the measurement was made, theory had predicted this red curve. Basically, the oscillations this is called a Fourier transform. It's a Fourier transform of the previous picture. It shows the power spectrum. And whereas the picture in real space looks kind of random, in Fourier space, it's anything but. It has these beautiful peaks and troughs. These represent the oscillation modes of the plasma as it came out of the Big Bang. You can think of it like a giant bell, and the Big Bang struck the bell, and these sound waves were set up, and we see these oscillations in the power spectrum. So the red curve was predicted in the 1970s, and then the observations were made by the Planck satellite around 2010, and other experiments, and they agree beautifully. Now, I was very fortunate. I got into this game before the experiments were done, and before all the theory had been worked out. So other people had calculated the temperature power spectrum, that's what it is, the power spectrum of this map. But nobody had yet calculated the polarization of the light. So light comes in transverse waves, and if a light wave's coming towards you, it can vibrate up and down or side to side or any combination. So there are two independent polarizations. And we calculated what the difference is between those polarizations, which is called the polarization of light. And here's the result, the red curve, which we computed. And you see the data just lines up beautifully. As I say, you don't often see pictures like this in basic science. This result is all the more surprising because there are no free parameters in the fit. Okay, once you fit this curve and you fit the parameters of the universe, which I'll tell you later, you just predict this curve. There's nothing you can do to adjust it, and the data lines up beautifully. This is the most recent data from this year, and there are now 15 of these bumps in the curve, and they all fit the theory perfectly. And I must say, we didn't do anything original in this calculation at all. We just turned the crank on a calculational machinery other people had developed throughout the 20th century. And the answer is what it is. So in a way, very disappointing. We didn't really learn anything other than our predecessors were correct. But this success of this calculation affected me very profoundly. It made me think, how simple is the universe? My goodness, we actually can understand it. We can predict its properties, and then they agree. You know, it's just bizarre on scales of 14 billion light years. So that has affected my point of view, and especially recently, I've become convinced that the universe is incredibly simple. To really understand it, we do need new concepts, but the ultimate picture is going to be completely comprehensible. That's my profound belief. Now, at the moment, to describe the large-scale universe, we only need 5 numbers. That's surprising in itself. It's not a complicated thing, the universe. It's incredibly simple. On large scales, the cosmos is nearly flat, so it's not curved. According to Einstein's theory of gravity, it could be curved like a sphere, or positively like a sphere, or negatively like a saddle, but it's not. It's flat. It's almost the same everywhere, homogeneous, and it's almost the same in all directions, isotropic. Why is that? Well, I'm going to give you a new explanation towards the end of this lecture. It's made up of stuff. The simplest ingredient is light, the photons we saw earlier. Then there are a certain number of nuclear particles per photon. That's a number. There's a certain amount of what we call dark matter. It's stuff which doesn't shine or interact with light. And there's a certain amount of dark energy. So those are 3 numbers, and I'll say more about these later. The structure of the universe, it has density variations, and we see them very clearly in this picture. They're at a level of 1 part in 10,000 on this hot surface, which emitted the light. So we need to understand that number, 1 in 10,000. Why is it 1 in 10,000? They are what's called scale invariant, meaning the density varies by a part in 10,000 on all scales, randomly and as what we call Gaussian random noise. It's the simplest possible distribution of density variations you could imagine. There's a very slight enhancement on large scales. Together, there are 5 numbers. That's it. So far, we have tons of evidence, lots of measurements, lots of fits to galaxy distributions, etc. No evidence for anything beyond these 5 numbers. However, at the same time as we've got these observations showing us this incredible simplicity and elegant economy in the universe, the most popular theory is anything but. The most popular theory is called cosmic inflation. Essentially, it's an idea that if you add stuff to the physics we know, you can make the universe blow up. Okay, a kind of cosmic explosion. And rather amazingly to me, most of my colleagues in theoretical cosmology believe in this. And there are tens of thousands of papers on cosmic inflation. In my view, no compelling prediction. And the worst thing of it is that this explosion, which you introduced artificially, is completely out of control on large scales. So this became a popular picture that instead of a universe, we actually live in a multiverse. And so our region might be this one, and we have one set of laws of physics, but somewhere else there'll be a different set of laws and the universe would look completely different, and so on. So people seriously propose this picture of the inflationary multiverse, which, as I say, is just wild, chaotic, out of control on large scales. And to me, that just smells wrong. I prefer to take nature at face value and try to figure out, what's happening based on that. So in my opinion, this is a dead end, this particular line of research. I prefer to go back to arguments which are maybe more traditional, where one looks at the observations, one makes simple mathematical theories and tries to fit. Now, I'll give you a parallel. Imagine we lived some time ago, a few thousand years ago, when people didn't know the Earth was round. Well, they thought the Earth was flat, very reasonably. And certainly if you live in Edinburgh, let's say, and you explore a small region around it, you would never have to worry about the curvature of the Earth. The Earth looks very flat locally in a local region. So you can ask yourself, well, why is the Earth so locally flat? Why does it appear locally flat? And the answer is because it's really very round, and you can see this in this beautiful picture made by NASA from space. You see the incredible smoothness and uniformity and spherical nature of it's not quite spherical, but it's very nearly spherical. The Earth is really like a polished marble, and because of that symmetry of the Earth, if you go in a small region, it looks very flat. So how do you explain that? Well, of course, a lot of people would explain it this way. Here is Thor, and Thor came along and made the Earth and hammered it into this beautiful symmetrical shape. And for me, this is a little bit like the inflation explanation, that, you just introduce something that does what you want it to do. There's no other evidence for that thing. And so, it becomes a sort of self-fulfilling story, which is not possible to verify. There's a much better explanation for the Earth, which is based on the following three things. First of all, the Earth is quite a big object. It's made out of many atoms, okay? Now, that doesn't explain why it's round, because you could think of your atoms as Lego building blocks and make a very big, complicated structure. And a priori, that would be more likely, because that's more random and has higher entropy. A sphere is a very special structure. So let's accept that the Earth is made out of many atoms. Now, gravity comes into play. We know that gravity tries to pull everything together. So that's very plausible, that's part of the explanation for why the Earth is round. But that doesn't really make the Earth round without another thing, which is dissipation. You see, when you pull rocks inwards like mountains and redistribute the rock and the molten rock and the solid rock, as you pull it in under gravity, there's friction. And in friction, the potential energy in the mountain is converted into heat. And heat has a vast amount of entropy. So that is always favored. Even though this Earth looks beautifully round and symmetrical, actually, because it's lost all of its structure to heat, all of its the parts sticking out have been converted into round object and heat. The heat has vast amounts of entropy. And so this is by far the most probable shape. And for the same reason, a water droplet, it tends to be round. And it's because the surface tension of the water pulls the water inwards, but dissipates its energy into heat. So thermodynamics is ultimately a big part of the explanation. Now, I went through all this because at the end of the lecture, I'm going to give you the same explanation for why the universe is flat. It turns out the universe is flat, I believe, because it's made of lots of stuff. And it's really as simple as that. Now, quite amusingly, just a month ago, a geologist in Aberdeen published some data providing evidence for this picture about the Earth, which is the following. You see, 2 billion years ago, there was an explosion of plankton in the oceans. And the plankton then settled to the bottom of the oceans And essentially, as sediments gathered, the plankton was crushed into carbon and graphite. Now, graphite, as you know, is very nicely lubricant, a very good lubricant, because the layers of carbon just slide over each other. And so this graphite was deposited in the rocks. And now when you had plate tectonics, you know, the Earth has its plates moving around, the continents move around on the surface of the Earth. When the plates collided, they could slide one above the other and make mountain ranges. And the sliding was possible because of the graphite. So whereas previously there was a lot of friction in the collision between rocks, life lubricated these collisions and made the mountains appear. And so this is really cute. And it explains that actually the deviations from this perfect sphericity or near perfect are because life lubricated, removed the friction, and created mountain ranges. And they've done a very comprehensive study of 20 mountain ranges around the world. And in each case, they find large deposits of graphite associated. So that's a lovely confirmation of that idea. Now, let's get to fundamental physics. And I apologize for showing equations, but after all, this is a maths institute. So that's what we do. Here are all the known laws of physics, and I've tried to represent them as compactly as possible. Here you see Einstein's theory of gravity. G is Newton's gravitational constant. F is for field, or like electromagnetic field, or force carriers. These are the fields which mediate forces between particles. Psi stands for particles, and this psi here is a symbol introduced by Dirac. And this same equation describes all the known elementary particles. And these particles interact through these forces, and they make up atomic nuclei and atoms and everything we see around us. Here we have the Higgs field. So I'm very fortunate to hold the Higgs chair. And so I will cheer for Higgs that he has more terms than anyone else in this equation. The Higgs field, you should really think about it like water. You know, if you think about a particle moving through space as if it was a fish moving through water, the water is what is what slows a particle. If I push a particle through water, you know, the water is resisting that motion. And the Higgs field does the same with elementary particles, and essentially makes them move more slowly than the speed of light. Particles which are massless, if they have no mass, have to move at the speed of light, like light itself. A photon is massless. But if you give it a mass, it prevents the particle moving at the speed of light, and it's as if the particle was moving through a medium like water. And that's what the Higgs field is. It fills all of space, and it slows everything down. And of course, that makes us and life possible. So here we have everything. And this formula, though, is pretty bizarre because it's a quantum formula. So here we see Planck's constant. This time it's in the denominator in an exponent instead of the numerator, but here it is. And the most bizarre feature is this imaginary number. Okay. So when I gave my inaugural lecture as a professor in Cambridge, my brother was there, and he's an economist. And at the end of it, he said to me, you know, honestly, if you're allowed to introduce imaginary numbers, no wonder you can do anything. But it's not like that. It's a terrible name. It's not really imaginary. It's absolutely real, and it describes the fundamental laws of physics. So what is this number I? Well, I squared is -1. So yes, somebody had to imagine that. But once you've accepted that, it's an incredibly powerful notion that there are numbers which are partly ordinary numbers, like the ones we're used to, 10.96, and partly multiples of this imaginary number, I squared equals -1. When you deal with numbers that way, suddenly mathematics becomes far more beautiful. You can solve all kinds of equations that you could not solve otherwise. So in particular, Euler, one of the most brilliant mathematicians in history, discovered this formula, which is that if you exponentiate an imaginary number, you essentially recover trigonometry. So the exponential of I times phi involves cosines and sines, which were of course known since the ancient Greeks and Indians, and you recover trigonometry. So as you should think about this formula e to the I phi, what it's doing is describing something going around a circle. When this phi comes back to 2 pi, you come back, it goes from 0 to 2 pi, you come back to where you started. And so going around a circle leads to this oscillation. And this is shown here that you can use it to describe a traveling wave. So this is the mathematics we use to describe waves. And for example, people who do electrical engineering and describe AC currents use imaginary numbers all the time, just as a technical device. But in quantum physics, it's really there. The I is there, and it describes the behavior of all the particles and forces. One way I like to picture this is just ripples on water. So here are these water waves, and you see if I threw 2 stones in a pond, the ripples go out, they interfere with each other, the waves can add or they can cancel, and all of this is described by this mathematics. So I really stands for interference, and interference is the heart of quantum mechanics. So in quantum mechanics, you add up all these quantities called phases. This integral means add them up. All of these numbers, the e to the I phi's, add up. They may add, they may cancel. And at the end of the day, you square the result, and that gives you the probability for anything to actually take place. So it's an amazing and central idea in all of physics. Now, actually, in these ripples, you see, if that's quantum physics, where's the Heisenberg uncertainty principle? Well, you can see that for yourself. If you poke a stick into a pond, you poke it in one point. And so you say, I want the water to be disturbed in one point. Well, you can do that. But one moment later, the disturbance will spread. You cannot localize the disturbance without giving it momentum so that it travels outwards. And this is exactly Heisenberg's uncertainty principle, that if I tell you where a particle is at one moment in time, you do not know its velocity at all. And a moment later, it could be anywhere. And so you can see this effect of the uncertainty in this analog picture in water waves. Now, let's solve some real problems. So this dark matter, what is it? Well, we can see it in a very similar way to the way you see water in a glass, right? So water is transparent. So how do you see it? Well, you see it because it bends the light coming to you from behind the glass. So it's easy to see if the glass is full or empty by the bending of light. In the same way, when we look at structures in the universe, this is a cluster of galaxies called a bullet cluster. The matter in this cluster of galaxies bends the light of the objects behind it, distorting the images, creating multiple images like drops of water on your fingers if you've just had a bath, distort the light behind them, and that's called gravitational lensing. And so we use that to see the lensing material. And when we do that, we see the dark matter, in this case, 2 lumps of dark matter, the blue. We can also study this in X-rays, and X-rays measure hot gas. And And in optical, we just see the regular stars in the optical. So in this case, there was enough information to infer the history. And what happened is that this blob of matter, this cluster, collided with the other one. That's why it's called the bullet cluster. This one traveled right through the other one. The hot gas which it carried was dragged through the other guy's hot gas and made this wake. This is just like the wake left behind a boat traveling on the sea. And so we can infer the whole history of what happened here from these observations. So through observations like these and many others, we really know this dark matter is there. What is it? Well, as I said, I'm always looking for the simplest explanation, and here it is. In the standard model of particle physics, these psis are these particles. We have quarks, we have leptons. The quarks make up atomic nuclei. The electron is the simplest lepton, and then there are neutrinos. And you notice three families, there are three columns here. And I'm going to tell you why there are three in a little while. There's the Higgs boson, which is coupling to them. And then there's these force carrier particles, nuclear forces and light. And in order to make this picture work, it was discovered in the 70s that you have to add right-handed neutrinos too. These are unobserved particles, which nevertheless influence the left-handed neutrinos in a clever way. And of course, we have gravity, which couples to everything. The way in which the right-handed ones come in involves interference in a beautiful way. So here I have a left-handed neutrino. It's a very light particle traveling along. And if this process didn't happen, it would be massless and it would be going at the speed of light, but it's not quite massless. The reason is it feels the Higgs particle for a moment and the right-handed neutrino. What happens is it oscillates. We say it oscillates. It means it interferes for a brief moment of time with the right-handed neutrino, and then it goes back to being left-handed. So there's what we call a virtual right-handed neutrino here. It only exists for a very short moment. The left-handed guy comes along, very briefly it changes into a right-handed one, and then quickly it realizes it hasn't got enough energy to be a right-handed one, so it goes back to being left-handed. The heavier you make the right-handed one, the less the effect, because it becomes more and more difficult to mix in this way. This is called the seesaw mechanism, and it explains why the left-handed neutrinos have very light masses, because the right-handed ones are very heavy. So using that, now go back to this picture. Where is the dark matter? And I think if you just come to this with a fresh point of view, you'd have to say it must be one of these. Okay, how could it be anything else? The right-handed ones, they don't couple to light, they do couple to gravity, they don't couple to nuclear forces. They're the obvious candidate. So it turned out we were able to make that work, but only recently. We showed that if the universe has this structure, instead of just our Big Bang, if there was an image universe before the Big Bang, and that's not really such a radical thing. You see, there's matter and there's antimatter. And in a certain sense, antimatter is just the mirror image, in a very precise sense. It's just the mirror image of matter. And one way of saying it is that antimatter is matter going backwards in time. Okay. And so this was really understood well before our work, but we went one step further and said, what if there actually was or is an image universe going backwards in time before the Big Bang? Turned out in this picture, we could calculate how many right-handed neutrinos were formed at the bang. And if they are the dark matter, we inferred what their mass must be. And it's 500 million times the mass of a proton. It's too heavy to make in an experiment, but nevertheless, this is a very precise prediction. There's a more interesting prediction, which is one of them is the dark matter, the right-handed guys. Then one of the left-handed neutrinos must be exactly massless. And that, it turns out, will be checked in the next 10 years. So what we measure so far are mass differences. We know there are 3 light neutrinos, and we know 2 of the mass differences. So you've got 3 numbers, but you know 2 differences. Well, if you know that the lightest one is massless, then you know all 3 numbers. And that's what we did. That's our prediction, that either the sum of the neutrino masses is 60 milli-electron volts. That's a 1,000th of an electron volt, very tiny, but still measurable. And that's if they're organized so that the 2 light ones and 1 heavy, then the sum of their masses will be 60 million electron volts. If it's inverted, so they're 2 heavy and 1 light, then the sum is 100. So that's a clear prediction. And amazingly, this is going to be tested in the next 10 years. Here's one of the many wonderful telescopes now being built in Chile, and their measurement forecast of the mass of the sum of neutrino masses is 12 milli-electron volts, whereas the prediction is 60. So we should be able to measure it at 5 sigma and confirm that in 10 years. So the Big Bang, it turns out, in our picture, is a mirror. It's not really the source of everything. Nobody introduced everything and blew it up. The Big Bang is just a point of reflection, much like a mirror. So if you look in a mirror, you see somebody, right? You see yourself. And just ask yourself, what's with that person? Because if you're right-handed, that person is left-handed. It's clearly not you, okay? But it's related to you. And so this idea of a mirror is actually a clever way of imposing boundary conditions in various problems. And often we use what's called the method of images to solve problems in electromagnetism by introducing this fictitious mirror image. And it's just the same in cosmology, that our proposal is that the Big Bang is a mirror, and behind the mirror is the mirror cosmos. And so our part of the universe is expanding, it's full of matter. The mirror cosmos is contracting and full of antimatter. And Mignon would have given his introduction to me backwards if I saw the recording of him in the mirror cosmos. It literally is a copy of us, except with everything reversed. Now, I'll tell you a little bit about dark energy. Here is a very expensive image of the dark energy made by the Dark Energy Survey. It cost billions of dollars to make this, but it's rather easy to reproduce because there's nothing in it. Okay, so this is what dark energy is. So just ask yourself the question, imagine you're Einstein, you're in 1917, and you want to make a picture of the universe, and you're wondering what to put in the universe. What kind of energy? So start simple. Let's have a kind of energy which has no structure. It's absolutely uniform in space, in time, and it doesn't even have motion. You know, like if I hold this cup up and move it, now it has kinetic energy. So it changes under motion. Imagine a kind of energy that doesn't even change, even if it's moving. So there's no meaning to its motion. Well, this is it. This is dark energy. It was called the cosmological term or cosmological constant. Einstein did introduce it to make a cosmos. It has bizarre properties. It's gravitationally repulsive. So whereas everything else attracts under gravity, this stuff causes the universe to blow up its size. And this was a cartoon from 1930 of Professor De Sitter, who is the person who solved Einstein's equations and understood this cosmos. Einstein made the cosmos static, actually, but this person understood the full time evolution of the cosmos. Here he is in the shape of a lambda, which is the symbol we use for the cosmological constant of dark energy. So the amazing thing is this very, very simple form of energy actually is the most dominant energy in the universe today. Today it's 70% of all the energy. Everything else is diluting away due to the expansion, but this dark energy doesn't dilute. It just stays at a fixed density, no matter how big the universe gets. Now the dilemma when you couple this to quantum theory is that the fields which I showed you in the standard model can't be set zero in the vacuum. Let me show you this first. All the fields in a quantum theory have 0 point energy. You can't set them to zero, just like I couldn't set, well, in quantum mechanics, I can't set anything, the position of a particle to zero, because if I tell you what the position of a particle is at some time, then I know nothing about its velocity and it will be traveling. And the best you can do is some kind of compromise where the particle is moving a little bit in the vacuum, and that's called a 0 point energy. The same with the fields. All fields have 0 point energy. Adding up all of these 0 point energies, because you can have so many little waves, gives infinity and spoils many of the basic symmetries of particle physics. So we have recently introduced a new kind of field called a dimension 0 field into cosmology. We actually did it motivated by the picture made by the Planck satellite. We want to explain that pattern that they see. It turns out explaining that pattern requires a certain type of field. And then amazingly, these fields cancel the infinite 0 point energies and the symmetry violations without any new particles. So it's a very minimal addition to standard physics, which has many remarkable consequences. One of the most amazing and surprising to us is that the cancellation of this 0 point energy, which this picture sort of captures, this is a computer simulation of 0 point energy in the vacuum. If you cancel this, which you have to in order to couple it to gravity, then it only happens if there are exactly 3 generations of particles. So I showed you those pictures with three generations of quarks and leptons. Turns out this only works if there are 3 generations, including 3 massive neutrinos. This is just an amazing numerological coincidence. And so we're very excited. We think that we may be on the right track. Here are the 3 generations, the 3 columns here, 3 generations. There is no explanation for why 3. Our explanation seems to, our mechanism seems to explain it. Now, I told you I'd come on to entropy. And we're now going to talk about the entropy of a cosmos, okay? So this is a very challenging conceptual problem. We're literally going to think about how many different ways could the universe have been arranged. If it turns out that our universe is the most probable among all those possibilities, or a universe somewhat like ours is the most probable, that would be a pretty great, a very satisfying explanation. Just like when we look around the room, or you look around the room you're in, you're not that surprised that the air is spread pretty uniformly through space. I mean, it would be a disaster if all the air molecules went into a corner of the room, leaving you in the vacuum, and you couldn't breathe. Fortunately, that doesn't happen because of entropy. It's much more likely for those molecules zipping around to spread them out uniformly. And that's how we understand why gases spread out. So entropy, we're going to do the same for the universe. Now, Stephen Hawking and Jacob Bekenstein initiated these calculations when thinking about black holes. And here's a picture that sort of illustrates it. See, a black hole is a very mysterious object where things fall in and then are lost to view. So we don't know what happened to them. We lose information. And so there's a lot of information that fell into the black hole, which we cannot recover because we can't see it inside the black hole. And that information loss is called entropy. And so Hawking managed to calculate, first of all, the temperature of a black hole, that it's like a hot object, like a very gentle fire, if you like. And associated with that temperature, he showed there was an entropy. The entropy you can picture as just being bits stored on the horizon. There's a little length called the Planck length, which I'll explain in a moment. And then every bit here can be 0 or 1. And so the total information is basically given by the area of the black hole in units of this Planck area and divide by 4. So there's and then the total number of states of a black hole is the exponential of the entropy. So it's really vast. So to do this procedure, Hawking used a trick called imaginary time. Again, it's this imaginary number. So those of you who've studied quantum mechanics knows that this is how things evolve with these Euler type formulae. And if you do statistical mechanics or thermodynamics, you use these formulae, which came earlier from Boltzmann, but they're very related. And so if you made the time a multiple, an imaginary number, a multiple of a real number, a real multiple of I, then you can convert this formula to that. And this is what Hawking did. He imagined time was imaginary and curled up in a circle. And they used this trick to calculate the entropy of a black hole and also the entropy of a cosmos, which had only dark energy. This is called de Sitter space, the same de Sitter I mentioned earlier. This is a picture of de Sitter space. Time is vertical, space is horizontal. And so this is like a sphere which shrinks to a small size and then re-expands. So they calculated this entropy and they found a vast number. For today's dark energy density, which is very small, you get an entropy of about 10 to the 120. It's really a vast entropy. And the way they did it is by curling up time, by making it imaginary and then curling it up. So really they used a 4-sphere instead of a 4-dimensional de Sitter space. And this they called a gravitational instanton. These are the technicalities which led them to this number. So we've recently generalized this to a cosmos which has both dark energy and radiation, because we want to describe the Big Bang. Surprisingly, this wasn't done before. It's really a simple idea once you realize it's important. And what we find is not this sphere, a 4-dimensional sphere, which Hawking found, but instead the symmetry gets broken and it looks more like a circle times a 3-dimensional sphere. Here's a picture of our instanton. And I won't go through this in detail, but essentially the picture is that if there's lots of entropy in the universe, the most probable universe is flat, homogeneous, and isotropic, just like what we see. And so the explanation here for why the universe is flat echoes the explanation for why the Earth is locally flat. It's just saying that this is a big thing. The universe is locally flat, homogeneous, and isotropic because there's a lot of stuff in it. I think that's the simplest explanation so far. Doesn't require any new physics, doesn't require inflation. It does require thermodynamics, and it requires Hawking's idea of gravitational entropy to be correct. I want to end by talking briefly about our place in the universe, right? So I've talked a bit about gravity and space-time. gravity is due to the bending of space-time. I've talked a bit about black holes. See, in black holes, the way to think of a black hole, it's really a waterfall, right? Imagine water flowing in, as in here, flowing inwards, where the flow of the water gets so fast that it exceeds the speed of light. And that means that any little boat on the waterfall, no matter how hard they row, they can never go back upstream. And so a black hole is really the flow of space into an object. When that flow exceeds the speed of light, nothing can ever escape. So that's a black hole. We can't see into the black hole. We're outside a black hole. And we now see black holes observationally, but we can't see into them. The dark energy, the stuff causing the universe to expand faster and faster, creates the opposite of a black hole. It's also a horizon, but this time we're on the inside. So anything further than a certain distance from us is traveling away from us effectively faster than the speed of light. So even whatever light it emits will never reach us. And so we're outside the black holes, inside the dark energy horizon. These are the two extremes of our vision. Now, I said I'd explain the Planck length. The Planck length is the following. Imagine I tried to see something very, very small. And I can ask, what is the smallest thing I could ever see? Well, the way you do it is you build a microscope using light, whose wavelength is shorter than the size of the object you're trying to see. And as you make that wavelength shorter and shorter, the energy of the light photon gets bigger and bigger. That was Planck's mechanism. But as the energy gets big, when that photon hits the thing you are looking at, there will be so much energy in such a small region of space, it will make a black hole and you'll see nothing. So that's the explanation of the Planck length. It's the length scale such that if you built a microscope to observe it, all you would do is make a black hole and you wouldn't see anything. So here we are. There's the Planck length. It's a very short distance, 10 to the minus 35 meters. The dark energy horizon is the biggest length we could ever see, 10 to the 26 meters. And here's the surprising thing I want to end with. Where are we in this universe between the smallest and the largest length? We'll take the geometric mean. Just multiply those two lengths and take the square root, and you'll find the size of a living cell. Life is in the middle, okay? We are in the middle of space, of time, of scale, of energy, and we are the most complex things that we know of in the universe. The universe is extremely simple on small scales, just a bunch of particles and forces. On large scales, it's this smooth, uniform structure. As it came out of the Big Bang, we formed small things first, nuclei. Then we formed galaxies, bigger things. Then the galaxies helped us form stars, in which we formed atomic nuclei. So there was this back and forth between small and large scales, and the back and forth ended up in complexity. So we are the most complex things we know of in the universe. We live in the middle of it all. Physics is easy on small scales, on large scales. It's really difficult on human scales because we are so complicated. Thank you. All questions are welcome.